Okay, section 2.5 is on advanced topics that you probably would not see in all computer network textbook. So when I'm trying to put this section, the material of this section, including spread spectrum, Ofdm, and MIMO, we consider again and again whether to put it here or not. But at the end, we put it here, but we put it in as an advanced topic in section 2.5. And in the book, I mentioned that if you do not have physical layer background, probably you can skip at first reading. At first reading, you could skip. But here, I still want to convey some interesting or key ideas so that you get to know the essence of this. In the homework, I think there are one or two. I think two questions. The F15 and 21 are on these topics. So I will skip some slide and yeah, I think I have half an hour left, which will be enough to cover this section. So let's talk about where should I start? Spread spectrum. Okay, the idea of spread spectrum is this. If your signal is transmitted with a narrowband spectrum, like this. So you have energy here, but no energy at the other spectrum area. Then your signal has a narrowband spectrum. It's quite centered at a carrier frequency, for example. Then what problem it might occur? If there is an interference signal comes in and hit you, if the interference hit you or the noise hit you, you are dead, because your energy is quite narrow, quite concentrated. So it's like because the other signal would hit you at a certain frequency. So if your energy is centered at that frequency, then you are dead. So your signal will be destroyed totally. However, if you spread your energy in a wider spectrum, say this, I spread my energy, and the energy is the same. The area, if you do integration, the size of the area will be the same as the size of this area. So the energy will be the same. However, you spread into a wider spectrum. It's called spread spectrum. Then the advantage is that if there's an interference or noise hit right here or right here, then it would only destroy a part of you, right? It would only destroy a part of your signal, not the entire signal. So the receiver might get, even if this is damaged, I still get the signal recovered back. So it's possible the receiver will be able to recover the signal, given that only a small spectrum area is damaged. Okay, so that's the advantage of spread the signal into a wider spectrum. And the remaining thing will be how to do that. Okay. There are several ways to do that, many ways to do that. But here, let's look at the first way. Okay, it says that, okay, this is the data, and I have a PN code, which is a sequence of chips. See, this is a bit. This is a bit, but this is a chip. Okay, so I have, within a bit time, I have 11 chips. Okay, and I have 11-bit Barker code, which stands for this pattern. So this will be this pattern here, 11 chips. And I do this, I do exclusive OR on this, I mean the data stream and also the chipset, I mean the PN sequence. This is called PN sequence, and this is called PN code. 11 chip will be the PN code, and along a sequence of PN code will be called PN sequence. And I do exclusive OR together, I will get this. See, I will get what? For this, 1, so exclusive OR with this. The 1 and 1 exclusive OR will be 0, right? And 1, 0 will be 1. So I have 0 and then 1, okay, and then 0. Okay, so I do exclusive OR to get this pattern. And if the next bit is 0, exclusive OR with this will be the same pattern of this. So this will be the same, the pattern here will be the same as the PN code. However, this will be different, and depending on the pattern, you will get this. So I got this. So I was here. This is my data stream. Now I become this. I break down into this. And this, in a sense, is a spread spectrum sequence that you spread the bit, the bit here into a sequence of bits. If this bit was hit by an interference, it's dead. But here, if this is hit by one particular, there's an error. If this bit is in error, then it's gone. But since I spread into 11 bit, if one of the bits is in error, fine. I will be able to recover what it is, as long as there won't be too many bits in error. If only 1 or 2 bits in error, then the receiver can still recover it. So in a sense, I'm spreading the bit into 11 bits. And that's called the PN code, the pseudo noise code, and the PN sequence, pseudo noise sequence. And then you will see, you will say, okay, ask one question: what pattern should I use? What kind of pattern should I use? The 11 bar code. What kind of sequence should I use? And it says that you have, depending on your code length, they suggest the Barker code. Okay. So if you have PN code, which is the 11-bit Barker code, then what you do is that you have a beta paired stream here, and you do exclusive OR with the PN code, and then you get this, and then next you do modulation, and then transmit. And again here the same. So you spread one bit into 11 bits, and the advantage is that you will be more immune to interference and noise. So this is the impact of interference and noise on direct sequence spread spectrum. It says that if the interference is narrow band, very narrow band, then after the spreading, the interference will become threatened with a quite low power density. and could be filtered out by a low pass filter. So it would have little impact on the data signal. And wideband, the same. Wideband interference and noise, also similar. So they can be filtered out. The noise or the interference will be flattened and filtered out easily, and they would have little impact on the data signal. And that's a direct sequence spread spectrum. And there's another kind of spread spectrum which is called frequency hopping spread spectrum. It's but less used because you can hop too fast. You can hop between frequency too fast. So the hopping frequency cannot be too high, meaning the number of frequency couldn't be too high. So here's how. It says that you still have a PN code. You still have the PN code generator, okay? And then this is the data signal. However, when there's a frequency wall and a frequency synthesizer tell you where you should transmit, which frequency or which carrier you should transmit your data signal. So you'll be hopping. So this sequence is generated with something like a random seed from a PN code. So the PN code will fit into this and then generate the frequency that the sequence of frequency hopping. Okay. So if I have a number of frequency here, so each one it will be a frequency channel. Then the PN code will tell me how I should hop the frequency. I would hop between this frequency with a pattern like this. I hit here first, and then here, and then here, and then here, and then here. So there's a pattern a sequence that you hop between frequencies. And why are you doing this kind of monkey job? Why you jump around between frequency? The reason is when you transmit, at this time slot, I transmit at this frequency. At the next time slot, I transmit at another frequency. Then if at this frequency, there's an interference or noise hit me, then it would only hit me for a very short period of time within that slot. I will be damaged for a short time. And in the next slot, I'll be transmitting at another frequency. And in another frequency, that might be clean. If that frequency is clean, I'm safe. So the damage will be partial, not all the time, just at specific slot time. So that's the reason why the transmitter hop around the frequency. And how it hops, or the sequence it hops, is determined by PN code. The PN code. The PN code will tell you how you should hop in between. And if this transmitter has one PN code and generate a sequence, and you have another, the same PN code but generate another sequence. So the sequence of frequency you hop will be different from the sequence I hop. I hop at say 3, 9, 1, 4, okay, and you hop at different. But it's possible that we would hop to the same frequency in the same time slot. It's possible. Then we will have a hit. But the chance of having that will be low. As long as there's the PN code. I mean the PN code or the PN sequence you generate and also the PN sequence you generate will have little autocorrelation, which is something called correlation. if the correlation between your sequence and my sequence is low, then the chance that we will hit each other, we will bump to each other, will be low. Okay, so that's the idea of frequency hopping spread spectrum. And it's still used in Bluetooth. The Bluetooth use this scheme, and also some wireless LAN standard use this scheme. But new wireless LAN standard does not use frequency hopping spread spectrum because its limitation on the number of frequency you can hop per second. I believe it's 1600 per second. You can hop 1600 times per second, but no more than that. Okay. So for low bandwidth, low bit rate, Bluetooth is fine. They stay with frequency hopping. But for wireless LAN, we are targeting for tens of megabit per second, or even 100 megabit per second in 11N. Then frequency hopping has its limitation, so it's not used in newer wireless LAN standards, but it's still used in Bluetooth. And again, this also spread the energy among what? Among different frequencies, right? Okay, I spread the energy, but the way I spread is that instead of spreading my energy to all frequency at the same time, I don't spread my energy to all frequency at the same. I spread them at different time. So at this time moment, I put my energy all in this frequency, but in the next slot, I put my energy into another frequency. Okay, so it's another kind of spreading the energy. Okay, CDMA is another kind of spread spectrum. It also, in a sense, that it also spread the energy into the spread spectrum. Okay, it says that unlike TDMA or FDMA, CDMA does not divide a physical channel into multiple subchannels. So each user would use the entire channel, the entire bandwidth of the channel. However, different users would use different PN code or orthogonal code. PN code and orthogonal code. Okay, so we have mentioned a PN code, so we know what it is. But what is an orthogonal code? So look at this. This is a coding scheme for CDMA. It says that if you want to transmit 1 bit, again, you transmit into this pattern. So it's in the sense that in order to transmit one data element, I need to transmit multiple data elements. Say in this example, it will be 8 signal elements. So I'm sending 6 signal elements in order to transmit 1 data element. However, I would use one pattern. And how about the others? Suppose we have 8 users using the bandwidth in this channel. Then it says that, okay, if I'm number 5, I would use this pattern to transmit a bit. And the others will use their own pattern. And we say that these patterns are carefully selected. They are carefully selected so that they are orthogonal to each other. And these patterns are actually vectors, the vectors. And what do you mean by 2 vectors are orthogonal? to each other. In the linear algebra, you know that two vectors are orthogonal to each other if what? Their inner product equal to 0, right? The inner product. So if you take a pair of this, so I take a pair of this, I do inner product. Okay, this will be 1, 1, 1, 1, and then minus 1, minus 1, minus 1, minus 1. So I have 4, 1, and 4 minus 1. The inner product will be what? 0, right? So these two are orthogonal to each other. And you can examine each pairwise. You can do inner product for any two of them. You will find that their inner product are all 0. That means that they are carefully selected so that they are orthogonal to each other. So what happens is if we add users here, each of us use one vector, and the vector we use are orthogonal to each other, then in a sense that we can transmit at the same time without interfering each other. The receiver, after receiving this, they will take the signal to the signal to do again the inner product to recover the data. Okay, and because the linear algebra tells us you can do that and recover the data sent by each user, even though they are mixed together. Even though they are mixed together, the receiver still can recover that because the call point they use are orthogonal to each other. However, the bad thing about this vector, the orthogonal vectors, are what? There are only a limited number of orthogonal vectors you can find. Given, say, 8-bit, you can find not many. You can, the number of vectors will be limited. So if I can have 8 vectors orthogonal to each other, then it means that I can only support 8 users transmitting at the same time, right? Can I support 10 or 12 or 20? No. I can only support up to 8 transmitting at the same time. So that's the disadvantage of having orthogonal code. And this is called synchronous Cdma. The synchronous CDMAs use orthogonal code, and they are only a limited number of orthogonal code, so supporting a limited number of simultaneous users. However, a synchronous CDMA says that I don't use orthogonal, I use PN code. And the PN code are selected so that they are statistically, the keyword is statistically, they are statistically uncorrelated to each other. Meaning they are in a sense that they are statistically orthogonal to each other. That creates a larger space for more PN code to coexist at the same time. So you can have, say, if I have 8 orthogonal code, but statistically I could have 16 or 20 statistically independent PN code. So the number of PN code I can use will be much higher. So I can allocate PN code to active users without a strict limit on the number of users, because as long as they are the PN code are statistically uncorrelated, the correlation is not too high, then I can use them. It's like talking about say if you want to have a paper reviewed. So for example, if the rule of the game is the paper should be reviewed by someone who does not know you at all. Then it's strictly limited. And another way will be I want to have the paper reviewed by someone who does not have conflict of interest with me. Then the reviewer might know the author, however, they don't co-work with each other. They don't have common interest. So then I can have that person review the paper. Then that creates more space, more candidates to find the reviewers. But if I say, okay, the reviewer should not know the author at all, then the choices will be quite limited. And here, orthogonal is a very strict property. You either orthogonal or not orthogonal to each other. So you either say, it's like another example will be male and female. The law right now in Taiwan, but in California it's different. The law in Taiwan says that for a couple to get married, they need to be one male and one female, right? They are orthogonal to each other. But in California, it says a couple does not need to be heterosexual. They could be one male, another male, two male, and two female. They get married. Okay, they are not orthogonal to each other, but they probably are statistically uncorrelated. Say they don't have the same source. They are not the same parent. If they are the same parent, if they have the same parent, it's forbidden by the law, right? I think even in California, they would not allow brother to marry sister, right? Okay, so as long as they are statistically or genetically uncorrelated, then or less correlated, the correlation is very low, they're allowed to marry. So you don't marry your cousin, you don't marry your brother, you don't marry your cousin, but you probably marry someone which have maybe 200 years ago you have the same ancestor 200 years ago, but the correlation will be very low, right? So the idea is as long as the correlation is not high, you can create more PN code to be used by multiple users. So the number of users will be less restricted. Of course, you can not have unlimited number of users. Then some of them will have correlation with each other, which is bad. Then they cannot use the spectrum at the same time. So that's called a synchronous Cdma. So if you say that so this is Cdma, they also have this property, but we have seen what the direct sequence spread spectrum and the frequency hopping spread spectrum, right? And they fall into what? Into this. So the number of users could be higher than this. This will be orthogonal. Will be you either are male or female. You can be in the middle. Okay. So this is a preferred choice for many schemes. That you use direct sequence spread spectrum here belong to a synchronous here, frequency hopping spread spectrum 2, and also the synchronous Cdma. Okay, so that kind of tell us the spread spectrum. Which have at least we have mentioned four solutions, right? 4 solutions for spread spectrum. And next we see Ofdm, which use multiple carriers instead of single carrier. Multiple carriers. So the input data stream here, and it's split into multiple stream, and each of them will be carried by a subcarrier. So there'll be multiple carrier modulator here. So the stream, the split stream will be, each of them will be modulated by a subcarrier. And then there'll be an operation called inverse fast Fourier transform. This stands for inverse fast Fourier transform. Then the operation will the purpose of operation is to combine those signal together to form a composite signal. Okay, and this is composite signal because it has different carrier of different frequencies. and then add up something prefix and then transmit it. And at the receiver, it will then do the fast Fourier transform to the reverse operation of this inverse fast Fourier transform here, and then get back the original signal, and then combine them together back to one stream. So these are the basic operation of Ofdm using multiple carriers. However, there's a for multiple carrier to work in parallel. There's a property that needs to be observed. It says that orthogonality of subchannels allows data to simultaneously travel over subchannels. So the carrier needs to be orthogonal to each other. So here we see the orthogonal again. And again, with orthogonal is a clear 0-1 clear separation. So the number of carrier will be limited again in Ofdm. The number of carrier will be limited. And then again, what you would ask, what does it mean by two signal or two carriers are orthogonal to each other? Two carrier which are orthogonal to each other. And this is to illustrate by this. See, I have a different wave, different sine wave. Okay. And they are orthogonal to each other if what? The crossover point. Two signals are orthogonal to each other if their crossover point is at the amplitude of 0. If their crossover point is at the amplitude of 0, meaning if they cross over here, say this, there are three signal, and they cross over here, and the crossover point is has amplitude 0. Then we say these three signals are orthogonal to each other. If their crossover point is here, then no, they are not orthogonal to each other. So, and it's a physical property that if two signals are orthogonal to each other, then what? Even if their spectrum overlap, they can still travel at the same time without interfering each other. So that's a quite miracle, right? If two signals having the same frequency but orthogonal to each other, then they can still travel at the same time without interfering with each other. So it would take it would take a while to appreciate that, and probably take another course in physics to better understand that. But it says that they can intuitively we'll think that if two signals having the same frequency transmit together at the same time, they would interfere with each other. But it says no, if they are orthogonal to each other. And the key lies in how can the receiver recover each of them. If the receiver can, then they are orthogonal. They do not interfere with each other. But if they transmit at the same time, can the receiver recover them? I don't know, but it says yes, they can recover. So let's just trust the result. Okay, so with that property, then things will become quite beautiful. That two people can share multiple signal can share the same frequency domain. Then you would have this, as we mentioned, that you split here and do the modulation and do the inverse Fourier transform. And then as long as the frequency are orthogonal, the frequency here are orthogonal to each other, then you can recover back. If they are not orthogonal to each other, it says that the first Fourier transform, say the Fourier transform theorem tells us you won't recover it if that property doesn't hold. The orthogonal property doesn't hold, then you can recover it. If that property holds, then it could be recovered. So not just by physics could tell us that you can recover it. And also the Fourier transform tell us you can recover it mathematically. It could be proved mathematically. Okay, and MIMO. Okay, MIMO is not a topic that is even younger than Ofdm. It's in fact, it's still a young topic. Still many ongoing research right now. So it's I don't know if you look at the data communication textbook that cover more physical area, physical layer. You probably won't see MIMO material in the popular textbook right now. So MIMO says that instead of just one, OFDM says that you can split the data to multiple carriers, multiple subcarriers. MIMO says that you can split the data to multiple antenna, and then the antenna array. This is an antenna array, and the receiver also has antenna array here, and another receiver here, and they can. Since the antenna array transmit the signal, and those signal, the sub-signal, traveling together at the receiver, because the receiver here, if this is transmitted through the antenna array, the receiver here would not just get the signal from the first antenna. It will get the signal from the other antenna too. So the signal will get this, and the signal here, the antenna here will all get the signal from all the transmitting antennas. So not just this is not one-to-one mapping. This is many-to-one, more like a many-to-many or many-to-one mapping. So from this antenna, it will receive the signal of this, and each of then this. So it's a cross matrix. It's a so I transmit, and all of them receive my signal, and again for this the same, and everyone have received some signal, but a little bit different, and everyone received all the other. So if this is m, this is another m. So m multiplied by m, you would, if you do some calculation here, you are likely to recover the signal back. I mean, each of them. Say if this is the signal is S1 to Sn, suppose this n, S1 to Sn. So you, from this, they are all mixed together, and actually you can separate them and then get back, recover the S1 to Sn back. And then if you got this, then you combine them together in another form, then you can recover the original signal. And that kind of operation or calculation can be done to recover the original signal, even though some part of the signal are damaged. So it provide even better robustness to damage in the channels. So that's the idea of MIMO. And I think I would not go further on MIMO, but you can tell that it's you would do convolution. If you know the engineering mathematics, there are a lot of operations which does convolution. So you can do convolution to if you have multiple source and multiple source and multiple sinks, and you can do convolution to combine signal together, and also convolution to recover the original signal. So that's actually mathematical operations. And there's an open source implementation on Ofdm, which is a component for 802.11a wireless LAN, and it does well. This part of the implementation, it is from opencourse.org, the same, and it's in hardware program. And the main component here is inverse Fourier, fast Fourier transform. However, there are some other modules that complicate the design. And in the textbook, I describe this module. However, if you are not physical layer people, it will be difficult to understand or appreciate them. But the key operation is inverse fast Fourier transform. But here, this is only the transmitter. This is the module for transmitter. And at the receiver, it would do this and also fast Fourier transform to get the signal back. And the fast Fourier transform or inverse fast Fourier transform, they all do this job, the convolution encoder. So there's in the book I describe how this convolution works, and it's put into a circuit. Okay, so in summary, here there are two sidebars at the end of this chapter. One is on cellular standards from the first generation to GSM to 3G, and then to 4G. And LTE is regarded as the promising technology, promising standard for 4G cellular systems. And you can take a look at what kind of modulation scheme they use. Okay, they use well, from the basic amps, the first generation they use just frequency shift keying, right? But here is I don't know what kind of shift keying it is. Okay, but it says that phase shift keying here, but it gets more complicated here with a QPSK or PSK QAM here in 3G. So right now we are using this, the 3G. Everyone here is using 3G. But next, what are we going to use? They'll be using QPSK QAM, the same. However, it will be higher. You got higher QAM, and also they use Ofdm to support multiple access. So these are the modulation schemes we describe are actually used in the standard in the real systems. And here's a comparison about LTE and WiMAX. So this will be mobile WiMAX and fixed WiMAX. This is a fixed WiMAX that this does not support mobility, and this support mobility, and they use OFDM and also MIMO here. MIMO. Okay, and LTE and LTE Advanced. Okay, they also use OFDM. And some small differences between them.